Hey, good morning. Happy Monday. So what we are going to do, we are going to get a couple of very interesting topics today. So the last thing that we did, remember, we were working on what is going to be considered to be a valid argument, not in everyday life, but in the, in the logical form. So we give you a definition. Let me just go to my notebook. Finish this one first to see. Yeah. You see, we talk about the valid arguments. Bring it up so we can talk about it again. The definition that we did, it was this one. Okay, the valid argument in everyday life, start with a line of arguments. We are going to call them P1, P2, P3 to the Pn. Okay, this is going to be the line of the argument, and there is going to be a conclusion. So we are going to say that that argument is a valid argument from our point of view if this implication that P1, P2, and the Pn implies C, the conclusion is going to be always true. Or this implication is going to be a tautology. So we have to list the information, the line of the argument, and the conclusion. Then sometimes it's quick to be able to identify it's a valid one, or sometimes we may have to use the truth table to prove that this implication is always a tautology. Okay, so this is just the definition of a valid argument. Let me give you some notation. Some people like to write it down in this format. They call it inferential form. Inferential form, you just break it into parts, P1, P2 to the Pn, therefore C, for example. C is the conclusion. So you should be able to read this type of notation because there are some problems in your book. Or you have a choice, you can use either one, okay? This is one notation or just inferential one. So we give a couple of examples of how we're going to try this one. Okay, so we give you one, especially the one that we use a contrapositive, so it's true. You can use the contrapositive version. That was the last one that we did. The line of the argument in symbolic form was if P then Q. That was the first line of the argument. So if you give me P, I do the Q and the not Q. So if these two is given to, the conclusion would be not P. So we want to check if this is going to be a valid argument. So the way we are going to do it, we are going to change the first one. Because if P then Q, according to the contrapositive law, is the same as not Q implies not P. So we change the given information into this format. If a not Q is given, then I get the not P. I've already got the not Q, so I should get the not P. You see, this is quickly by the contrapositive law, we get to the result that this argument is going to be valid. Okay, any question? So let's get to a little bit of some tricky one. This next one is very popular and it's easy to answer, but you must make sure to get it right. It's one of those things that when you use everyday life argument, you may think that this is true. But when you use logic, then you realize that this is false, okay? So it's one very popular example. Let's see. So the line of the argument is the following. If Mary wears, if she wears the green hat, okay, the green hat, she will lead the bands, okay, then music band, etc. Okay, then she leads the band. So that's the first part of the argument. Okay, that's the first line. The other one is Mary doesn't. Okay, she doesn't wear the green hat. The green hat. So that's going to be the second line of argument that we are going to have. So what is going to be the conclusion? So most of the people conclude that, therefore, okay, therefore, she doesn't lead the band. Mary. Okay, that's it. She does not, if you like, this is it. She does not lead the band. Lead the band. You see, this is in everyday life, seems to be a very nice and correct conclusion in this case. But if you put it into the format of a symbolic one, then you see that this is not going to be valid. But we have to, we have to prove it. Okay, are you ready? Change it to the symbolic form. The first one, Mary wears the green hat. We may call this one P. Okay, she leads the band, so we call this one Q. Okay, it's going to be Q. So for the first part of the argument, we have the fact that if P, then Q. Okay, this is going to be the first one. Now the second part, she doesn't wear the green hat, so it's going to be not, okay, so this is going to be not P. So, and the not P. Okay, so what is going to be the conclusion? The conclusion is going to be, this is it, therefore Mary does not lead the band. Does lead the band is Q, so this is going to be not Q. Okay, it's going to be not Q. So this is going to be the one. Make sure that you're not going to be confused with this one. You see, in this case, that was if P then Q and the not Q. You use the contrapositive, you get the not P right away. Look at this one. This is if P then Q. If P given to, then you get the Q. Now not P is given to you. You want to get the not Q. Remember when we talk about the inverse of an implication? The inverse of the implication, if you remember, was inverse of the if P then Q was not P implies not Q. And we just, we give you example that this is not going to be equivalent to each other. If P done Q is not equivalent to the not P not Q. So that's why this type of argument is not going to be a tautology, but we have to prove it. Okay, so what we have to do is you have to check to see if this is going to be, okay, the line of the argument is going to be if P then Q. This is going to be a first line of the argument, okay, and what? At the not P should implies a not Q as a tautology, okay? 2 lines means tautology. So this means regardless of whatever you do to the P and the Q, this must be true, okay? So this is not going to be true, or, if you want to prove it, to check it, you need a table. You need a table to be able to talk about it. You can draw a full table, or you can draw one line to show that this, okay, the truth value of this implication is always false, okay? So if you want to do it briefly, some people, they do it totally. You don't have to, but it's okay. If you want to write it in full form, so let's see what we need. We need a P, we need a Q. Okay, we need if P then Q. Okay, to get to this part, then you need the not P. This is going to be the not P. Okay, then you need to put them together. So it's going to be if P, then Q, and, okay, and not P. Then you need the not Q. Not Q, and you get to the conclusion. So your conclusion is going to be, you can write it, a Q or something, but or we can have it if P then Q, and not P implies, okay, not Q. So if in this paper, table you get an F here, you reject it right away. Okay, so you can try all the cases, or just quickly just do it. Okay, so for example, this is a conditional implication. You know that the conditional implication would be false. Remember, it's false. So if this is true, but this is false, true, false. So what you need to have is you need the not Q to be false. So that must be false. So you have to pick the Q to be, okay, pick the Q to be true. If you want to do it quickly, otherwise you can try all the possibilities. Okay, if you pick the Q to be true, then the not Q would be false. So this is false. Now what you are going to do is you are going to make this one to be true. Okay, in order this one to be true, you have to have both of them to be true. Okay, to have both of them be true, so the not Q must be true. So this must be false. So if you check it, you will get it now. P is false, Q is true. So we start with the false statement, so it's always true. Okay, and both of them are true, so this is going to be true. So the first part is true, the second part is false, so this means this is false. And you stop here. Any question? You know, if you miss it, draw the table to, you know, all the cases. But that's quick, you can get it right away. Otherwise, you know, true, true, false, true, true, false, false, false. You will get this. At least you get one case that this is going to be false, but that's quick. You can find it. Okay, I repeat it again. You want this implication to be false. The only time that this is going to be false if the first part is true, the second part is false. So your not Q must be false, so your Q must be true. So you have to make this one to be true. Both of them must be true. So the not P must be false. Not P must be true. So your P is false. Automatically you will get all of them. Okay. So this is it. Your implication is not a tautology. So therefore your argument is invalid. Okay. So the argument, this is it. The argument is going to be is invalid. In your book, I told you the other day, they just use some Latin expressions for all of them. I think they call this one the inverse error. They say by the inverse error, this argument is invalid. But we want you to show us really that's one. Okay, but generally they say inverse error. Inverse error is that this is it. If P then Q, the inverse would be not P, not Q. They are not equivalent, we know it. So you cannot get it. But it's nice to write it down for us on the test. We don't need a full table, but if you give us the full table, that's it. It will be fine. But we need one case to be false. One case to be false. You can find it quickly or just write a couple of format of your table and then you'll be done. Okay, any question? So that's a very popular case. You see, when you talk about it in everyday life, you may think that this is a true argument. Mary does not wear the green hat, so therefore she does not need a band. Okay, when we talk about it in everyday life, this is just a conclusion that we have it. But we have to use our model, okay, our language, our communication method. Our communication method, this is going to be the one. This is not going to be a tautology. Therefore, this argument is going to be invalid. Okay, any question? So this is the one that you will see most of the time. Let's have another one, a little bit more involved. So we give you 4 of these as 2 questions on your next test. A couple of them would be like this one, but sometimes you may have a little bit more. Okay, and I have some method, I call it algebraic method. You may like it. So I'm going to show you one of them with this example. So what's the next one? The next one is this one. Either, whichever. Okay, either elephants. That's going to be the one. Elephant. Either elephants are blue. Okay, are going to be blue, or monkeys are green. Or, okay, monkeys. Or monkeys are green. So that's the first line of the argument. Okay, elephants are blue or monkeys are green. So it's going to be the second part. The second part is just the elephant. Okay, elephants. Elephants are gray. Are gray. By are gray, we mean not blue, of course. Not blue. Okay, this is going to be your second line of the argument. So what's going to be your conclusion? The conclusion is that therefore, okay, therefore, monkeys are green. Are green. So this is the line of the argument that that we have over here. Just try to see if I can focus this one better. Okay, we get better one on the first one. So let's try it again. Yes, we got better one. Okay, are you ready? So change it to the symbolic form to see what you have in this case. Solution. So elephants are blue. You may call it P. Elephants are blue, or monkeys are green. You may call it Q. So the first of our line of the argument is going to be P or Q. So it's going to be the first part. The second part, elephants are gray, which means they are not blue. So this is going to be not P. Okay, so it's going to be not P. And therefore, what you want, the implication is the monkeys are green. Monkeys are green means just Q. Okay, so what you have to prove? You have to check to see if P or Q and not P implies Q if this is going to be a tautology. So that's going to be the question. Okay, any question? Now, one way to do it, just draw a table. Okay, draw a table and show that this is going to be a tautology. So let's go with the table. Then I give you a shortcut for this one. You say you need a P, you need a Q. Then you need a P or Q. This is going to be P or Q. Then you need a not P here. That's going to be not P. Then we need to form this one if P or Q and not P. Okay, then we get the implication, which is going to be P or Q and not P implies Q. So that is what you have to do. Just consider different cases. You have 4 cases for the P and the Q, and show that in all cases you end up with a true statement. Okay, are you ready? So true. That gives you true here. So this would be false. This is and, since this is false, this is going to be false, and you start with the false statement. You don't care about the other part. This is true. Okay, and you check other possibility. This is going to be true, false. A P or Q, one of them is true, so it's going to be true again. Okay, and the not P is going to be false. Again, since this is false, this would be false, and you start the implication with the false statement, so the result's always true. Okay, the other way around, you start with the false or true. One of them is true, so it's going to be true. Not P would be true. Okay, so in this case, both of them are true. This is going to be true. This is true, and the Q is also true. So that gives you true again. Okay, and the last part is false, false. So both of them are false. This is going to be false. And this would be true. But since the first one is false, so this would be false. And you start with the false statement, the result is always true. That's it. So your statement is going to be a tautology. So this means the argument is going to be valid. The argument, okay, is going to be valid argument. And with that. Okay, any question? Now, there is a short form of these type of problems, especially when we get this if P or Q. It's useful to know it. It's optional. You can play it safe all the time and use, okay, use your table for the test, or, this is not bad. So I'm going to call it method 2. Okay, any question on the first one? It's usual one, and we can apply it all the time and we are fine. But if you like algebra, I give you one. You see this method. In this method, we are going to use this fact. You see, I just remind you that, recall that. Remember, this is the one that we use even on the quiz, and we are going to use it in future. We talk about it. If P then Q is what? Is equivalent to the not P or Q. You see this? So if you have a kind of just or combination, you can change it to the this conditional implication or the other way around, and that would help you to be able to do these problems nicely. Okay, so what we can do is for the given problem. So for the given problem, what I'm going to do is this one. So you note that I'm going to work on the first part. You see this first part that is given to you. So I start with the fact that I have a P or Q. P or Q, I want to change it into this format. I need something like a not P to be able to do it. So this is going to be equivalent to remember the double negation that we talked about it. Instead of the P, you can write a P not P, remember? Not P. So not P would be just not P and Q. Okay, so it's going to be not P and Q. In this case, look at this one that we have. So if you have a not P or Q, it's going to be P or Q. So you have something like a not P. This is going to be your first term, not P or Q. So it's going to be equivalent to the not P implies Q. Okay, when you write it in this format, whatever it is over here, you have to have its negation. So exactly what we did, we have the negation of a not P. So we start with the not P, then Q. Okay, any question? Now go back to what you have. Look at this one that you have over here. So you have what? So you change the first one. So you are going to have this one. So we have, if you like. So you have that not P implies Q. Not P implies Q and the not P. Not P and you want to implies Q. So automatically we get it. Because if I give you not P, you give me Q. I've already given you not P. So I will get the not Q and then you're done. Okay, so I write one more line. So we have the first one is if P or Q implies a not P. This is the one that you have. So what we did, we just change it into this format, and this format automatically give you the Q. So this means if P or Q not P implies Q right away, and the valid is when the argument is okay. The argument is going to be valid. Okay, if you like this type of algebra method, we got it, that we put them together. It's nice to know. Okay, and most of the time they are going to be in this format. You can check it, but if it's going to be on the test, on the quiz, you see if you are not sure about it, So because the table, you see, the table would give you the answer all the time. And if you are short in time, you can check that one. But it's nice to know this type of method. Okay, any question? So this is one case. Now I should give you one with the 3 variables because that's a P and Q. So we should have one with the 3 variables and usually give you one question. So these are optional, but it's nice to know this type of methods. So we need this one as a last one, if you like. If you get time, we give you more, but we have quite a lot in the practice one that we are going to have. Okay, let's see how we're going to work with the variables. Are going to be more than 2. So this is it. The example is if I work, okay, if I work, I can, if I work, I cannot study. I cannot study. Okay, so this is going to be the first line of argument. If I work, I cannot study. What's the second one? The second one is either. Okay, the second one is either I study, or, okay, or I pass mathematics. I pass, math course, something, mathematics. Okay, so it's going to be the second part. Either I study or I pass math. So it's going to be the next one. The next one is I work. Okay, I work. So it's going to be the conclusion. The conclusion is going to be therefore. Okay, therefore I pass mathematics. Therefore I pass mathematics. It's the one that you have, you have one more symbol, if you know, or one more proposition. You get these steps. Okay, are you ready? Put that into the symbolic form to see how many symbols you need. If I work, we call it P. Okay, I don't study. I'm going to call this one not Q. Some people, they call it Q, then they go on, doesn't matter. And not Q is better. So the first part would be changed into what? So the first part would be if P, okay, if P, not Q. That's the first part, okay? The second one, if I study, so that was a not Q, so there's going to be Q. Okay, either I study or I pass maths. So this is a new one. So you have to call this one something new. So I pass maths, you call it R. Okay, so the second line of argument would be a Q or R. Q or R. Okay, what's the last part? Therefore, I pass mathematics. Okay, I pass mathematics. So this is going, oh, I'm sorry, I missed one of them. I work. So I work means P. If these all happen, so the conclusion is going to be what? The conclusion will be I pass mathematics, so it's going to be R. Okay, so this is where you need, you need the 3 proposition. Any question? Now, what you have to prove? You have to prove that this is it. What is the proof? So the first premises is if P not Q, and the second one is Q or R, and P. That should implies R as a, okay, as a tautology. So this must be true all the time. Okay, so one way to do it is what? Just doing the table, which is very safe. Takes a little bit more time, but you will get it right. Okay, so get your table and we continue. This is it. You need enough space to be able to cover all of them. Okay, so this is it. So this would be our P. This would be Q. Okay, PQR. PQR, then you have to have a not Q here, not Q. Okay, not Q, then you have to have the P, then not Q to cover this part. Then you have to form the Q or R, Q or R. Okay, this is going to be Q or R, and you already got the P, so we can put them together. So it's going to be P, not Q. Okay, P not Q, and okay, P not Q, and what? And Q or R. This is it, and P. And P, and the last part is going to be the conclusion. Okay, it's going to be quite a lot. I'm going to call it, I'm going to call this one Q. So you may call all of them. We do it even on the test. If you have enough space, you can do it, but we accept it and we understand what we are talking about. Okay, any question? So we have to write this one as the last line here, which is quite a lot. So I'm just call it Q, and then we have it and we can take care of it. Okay, you have three propositions, PQR. Each one would have two choices, true or false. So two choice for the first one, two choice for the second one, two choice for the third one. So you have 8 choices. Okay, just make sure you don't miss it. You have to consider all the 8 cases. Okay, are you ready? The case 1, all of them true. If this is going to be true, this would be false. Okay, this would be false. If P, then not Q. You see the P is true. The P is true, but the not Q is false. So this would be false. You see, when this is false, remember this part would be false altogether. You don't have to continue. The starting point is false, so everything else is going to be true. You see, that's fine. We can write it down if you like, but you don't need it. Because if P, then not Q is going to be false. So this implication starts with a false statement. Any implication that starts with a false statement is always true. If you don't believe it, so P or Q would be true. You see, and again, this one of them is false. So this is false. You see, this is false, and the result's going to be true. Okay, any question? That's one case. You have 7 more to go. True, true, false. The order is not important. You can do whatever you like. Okay, the not Q is going to be false. Not Q would be false. Same thing. You see that P is true. This is false. So this would be false. So since this is false, automatically this would be false and this would be true. Okay, this is also true, but you don't need it. Okay, and then we continue. This is going to be true, false, true. Okay, that's a true, false, true. So the not Q is going to be true. Okay, P not Q, that give you true again. But Q or R is going to be true. P is true, so this is going to be true. R is also true, so that give you true again. Okay, question? Move on. The next step is going to be, we go with the false. Okay, that's it. False, true, true. False, true, true. So the not Q would be false. Not Q false and the P false, so this is true. Q or R, both of them are true. So this is it, and the P is false, so this would be false because the P is false. So when it's a false, you know that the result's always true. Okay, so this is 4 cases, 4 more cases. So the next one is going to be, this is, maybe I go for it. I get a false, 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 true. So the not Q is going to be true. Okay, P is false, so this is always true. Q or R is going to be true. And the P is false, so this is going to be false. So since the starting point is false, this is always true. Okay, and the next one. The next one is going to be T, false, false. Okay, the not Q is going to be true. P implies not Q is true. Q or R is going to be false. So this AND combination would be false, so everything is true. Okay, and the last one is if all the threes are going to be false. Okay, the last one is if you get a false, false, false. So the not Q would be true. If P not Q start with the false, so this is going to be false. So everything over here is going to be false. We don't care about this one. It's always true. And if you want to have it, QR is also false. So as you can see, this is it.
You're missing one.
I did?
Yeah.
Which one is it?
You need
1, 2, 3, 4, 5,
FTF.
6, 7?
Yeah,
Oh,
you
this one.
need FTF.
F. What's the other one?
FTF.
FTF. Thank you. There's so many of them. FTF. Okay, so the not Q here is going to be false. P not Q, when it's start with the false, so this is going to be false. So this is always true. Okay, you know, if you want, QR is going to be true. And this is false. Okay, so we get it. So the argument is going to be the argument is going to be is valid. Okay, any question? You can use that shortcut for this one nicely. You see, look at this one. To use a shortcut, this is Q or R. If you change this Q or R into the implication, quickly you can get it. You want to try it? Any question on this one? You know, this is it. You have to be patient to get it. But if you want to have a method 2, okay, method 2, again, I remind you that, okay, recall that if you have if P then Q is going to be equivalent to the not P or Q. So what I'm going to do, I'm going to simplify this one because I simplified Q or R. Q or R, to change it to this implication, I need a not Q or a not one. So this is going to be not Q or R. So that quickly give me what? Not Q implies R. Okay, not Q implies R. So if you go back to this part, you see, look at the one that you have. The first one is if P, then not Q, I just changed the second one. Now you have, okay, we have, what we have is, we have a P implies not Q. And the second one, we change it. We change it to the not Q implies R. We have something, we call it the transitive property. Transitive property is, you see, you have if P not Q implies R. So the middle one would be dropped, and that give if P, then Q, then R. Okay? So if P not Q and the not Q R, so that would implies if P then R. So what you have, you go to your original one. You see the original one. Instead of these two, you are going to change it into, you change it if P then R and the P. You see, I changed the first two into the If P then R and the P. So what does it mean? This means I give you P, you give me R, but I already got the P. So I will get the R. I get the R. So this means we call it by transitive law. Transitive law. The argument is going to be is valid. You just drop this middle one if you like. We are going to see this law when we get to the, we can write it down. It's the transitive law, if you like. This is a transitive law. You see, the transitive law is if P then Q, and Q then R, it's the same as P then R. That's a transitive law. If the middle one is the same, it's kind of, you can drop it and you get the other part. You see, this is a nice one if you like algebra or just this type of operations. It's it's a good to know, but it's not the case that always can be applied. But if you have this OR combination, you see the key is this one, and to be able to change it to get to this. Most of the time it's going to be possible, but as I told you, just play it safe for the test. You may check it with the video table to get the number done. But it's a nice method. There you are. So be patient. Be able to go through one of these three variables parts, if you like, three propositions. But it's not bad. Okay. Any question?
So
yes.
If we take the second approach on the quiz or exam, are we supposed to state the by transitive law? Do you actually want us to write that down?
Yeah. That's the key.
Okay.
For this one, because they question you. How do you know you know that it's like, yeah, you have to give us that.
No, I'm just saying, instead of just writing all the steps like you have, we actually have to state by transitive law.
Oh, all together? No, you have to create it. If you create this part, yes, the rest are going to be followers.
Okay.
But cool. You have to create the transitive law. You don't need to do this. Okay. And that's it. It's done.
Okay, cool.
But you have to create that part. We get to the transitive law for the sets when we get to chapter 6, but it's very good in logic we also use. Okay, so that give you the one that you have to be patient. Your book, they are very much interested in this step. They give a number of them in your assignment, so be patient to go through it. And there are a couple of them in your book that they give you the solution at the back, but it's not correct. I'll let you know. There are 2 in your book, part of your assignments. They give you the symbolic format, and they ask you to check whether it's going to be valid or invalid. But there are 2 of them that at the because the people asked me before this one, but I'll let you know when we get to that part. Okay, so there you are. We are done with the valid argument. It's very important, so that we'll tell you that when you get to do this type of idea, you have to stick with the rules of the logic. Okay, not your interpretation or everybody's interpretations, because you have to do this type of argument with your machine or to communicate. So we got to be careful. Stay with the rules of the games, if you like. Okay, and go for it. So that is what we need for that. Okay, we are done with chapter 2. Yes, that was chapter 2, and that was 2.3 that I talk about it. That was 2.3. We have some nice problem in your book. Just check it, and you will see your practice test quickly. Test number 1, 2 questions, 4 parts of the valid argument. People mostly get it right away. Have nothing to worry about. Okay. Any question? Now, what's going to be the next chapter? This next chapter is going to be quite interesting, not difficult, but it's very fundamental. The way we write and we argue for the rest of the course. Okay, the way we write the proofs, because you have eventually we are going to prove things. Okay, we give you the theorem, and then we want to prove our theorem. So how we're going to check or write it down, this type of proof. So remember, if you are in algebra, so what we did so far, we are building up a new language, if you like, okay? So our language is the logic, and the alphabet are going to be propositions, okay? P, Q, R, etc. So we define so connectives, put them together, and we give all these type of ideas. So we have a new set, if you like, the set of propositions, if you like. If you are going to be in algebra, the set that you usually use in algebra is what? The set of real numbers. So when you stay with the set of real numbers, then you are going to propose, or you're going to define variables. Okay, we define X, Y, Z that can stand for any real numbers, and we call it a real variable. So when we say X is a real variable, this means X can stand for any number. So that's going to be X. When we get the X, then what we do is we are going to define a kind of a function of X. Okay, and we know it, a function of X. X is going to be the input. So a function of X is going to be kind of a combination of the mathematical operation that we do, we get the result. So what we are going to do in this chapter, briefly, we are going to define a kind of functions. Okay, we are going to define a function on these proposition that we talk about it. That function, okay, is going to be called a predicate. I'm not going to call it a function. So they are propositional functions, which is a function that's defined on a proposition, or predicates. So that's the idea of this chapter, the definition and application. That's going to be 3.1 up to the 3.2. Let's see if we can do all of them. There's not much in it, but the conclusion is going to be huge for the rest of the course. Okay, so what we are going to talk about it, we are going to talk about predicate. That's the expression that we're going to use. Okay, predicates. That's going to be predicates, there's a E here. Predicates or propositional, this is that I call it. Or this is going to be propositional functions that give you a better idea when we define it. Predicates or propositional functions. Now what's going to be this one? That's it. So is like a function that we do. So a predicate or proposition is going to be a statement containing variables. That's it. A proposition that contains a variable is going to be called a predicate. Okay, so a predicate or I just propositional or a propositional function is simply a statement, is going to be a statement, it's going to be a statement containing variable or variables, containing variables, that's it. So if you're a statement containing some variables, we are going to call it predicate. That's it. Example, we reject at the beginning when we talk about proposition, we did have some of them, but we say, oh, it's not a proposition. Now we have a name for it. So this is it. The following. Okay. The following are predicate. The following going to be predicates. That's it, the first one. You see the first one, x plus 2 is equal to the 7. In algebra, you call it an equation, but over here we call it a predicate. Because it's a statement. This statement can be true or can be false, of course. It's a proposition. Okay, it's a statement that contains a variable. What's that variable? Variable is x. You can say that is a predicate with one variable. Okay, it's a predicate with one variable. Okay, any question? Another one. Another one is X is France. X is France. Again, it's a statement. Since contain a variable, we say, oh, this is a predicate. So another one. You may have more than one variable. X plus Y less than equal to 10. Again, this is a statement containing two variables. So it's going to be a predicate in two variables that we get, or a function. Okay, so these statements are going to be called predicates or propositional functions. Any question? So you need to have the variables. So it's kind of function, as I told you. And so we have a function, functional notation. We have the f of x, for example, for the usual function. But since this is a predicate, instead of f of x, we usually use p of x. So let's have the notation that we're going to use. Okay, so it's going to be notation. Notation for the predicate. That's it, like a function. So we may have a function of several variables. Now we have a predicate. So a predicate. Okay, a predicate P. Predicate P containing n variables. N variables. N variables, as usual, you may call it x1, xyz, x1, x2, x3, okay, etc. up to the xn. It's going to be a function of n variables. It's going to be denoted. Okay, it's going to be denoted by the notation is going to be like a function notation. It's going to be p of what? P of x1, x2, up to the xn. Okay, when it's a two variable, as usual, we call it p of x, comma y. If it's going to be three variables, we call it x, y, z. Okay, so this is just a general format that we're going to have. So this is going to be a predicate with n variables. Okay, and so special cases that we're going to use. So if I give you p of x, comma y, comma z, this is going to be what? A predicate in three variables. It's going to be a predicate. Okay, this is going to be a predicate in three variables. Okay, three variables like algebra. Three variables, x, y, z. Okay, so again, therefore, if you see this type of expression from now on, therefore, if they give you px, you know there's going to be a predicate in one variable. Okay, you may be giving q of, you can use different names, x, y, okay, etc. There are going to be notation for, okay, are predicates in this chapter. So it's going to be predicate. Any question? So it's a kind of function notation for the propositions. Okay, what next? You know that if you have a function, of course, we have a domain of the function. So in these arguments are going to be the same thing. So if you want to have a predicate is going to be p of x. So we have to give us the domain of the function. The domain of the function must be given to us so that we know that what type of the values, you know that, what type of values can you assign to the x. So when you see this type of arguments, you have to check the domain. The domain would be given, and it's important because if they just change the domain, the property of your proposition may be, or the predicate may be different. So this is one thing that you have to be careful. Okay, so defining the domain, set up all the inputs or the x. Okay, so a set of values, numbers, in which these variables can assume, if you like, in which the variables in a predicate, variables in a given predicate, may assume can assign if you like to. Okay, may assume their values. That set of numbers is going to be called the domain. It's called the expression is the universal domain, which is called a domain. Universal. Okay, universal domain. That's the expression, the domain of this course. Okay, the argument that we're going to talk about it, or simply for us is going to be the domain. Okay, the domain of the predicate. It must be given. Okay, so it's going to be given. It's not like a function you're going to find it for us. So these variables that we use, we have to tell you that what's the domain of these variables. Okay, what type of numbers can you use? And it's very crucial. Sometimes they change it. So you have to read it carefully when you deal with this type of problem. The domain is going to be usually, it's going to be either counting numbers, or the natural number. You may have integers or you may have all real numbers. But when you check the problem, you have to check the domain first to make sure you get it right. Okay, any question? So that's a notation that we're going to have. Let's see how we're going to work with this notation. We give some statement, you have to change it in this symbolic form for us, or the other way around, and you have to work with it. A function would be given in algebra. You find what? F of 2, F of 3. It's the same thing here. But there is always an extra aspect of this problem. And that aspect is this result is a proposition. Okay, so it may be true or may be false. Let's see what's going to be this example. So for this example, suppose you have the following. Suppose the domain is n, as usual, positive integers, or is the set of all natural numbers, counting numbers of all 1, 2, 3, 4, 5, 6. That's what we mean. Natural numbers. Okay. And let this is going to be your predicate. And let, you see, this is the way you're going to be given p of x comma y. You are not going to write equal to. Remember, because this is an statement. So they give you p of x, y. This is the way you write it down, the point here. And then x plus y equal to 12. Okay. Remember, this is a statement. So the statement that we call it p of x comma y is that x plus y equal to 12 in the domain of all counting numbers. Okay. So suppose this be given to you. Okay, so this is going to be your predicate. Now then let me ask you some question. Then they ask you to find some values of this function for us, okay? So what we would like to do is, any question on this one? Are you done? I have to go to the next page. So this is the statement that's given to us. Then there may be some question, ask two questions like in algebra. So for example, if this is going to be the case, then you see, then this is it. Then, for example, if you've been asked what is the p of 3 and 9? P of 3 and 9 means you are going to use x equal to 3 and y equal to 9. You go to the equation of the statement. Remember that was x plus y equal to 12. So your x is 3. So this means 3 plus 9 equal to the 12. Okay, this is going to be your statement. Now, as you can see, 3 plus 9 equal to 12 is a true statement. So we can say that so P3 and 9 is what is true. So this means this is going to be a true statement. Remember, it's a proposition. So the proposition can be true or can be false. Okay, any question? But suppose you've been asked to find P2 and 5. So if you want to consider P of 2 comma 5, this means your X is 2 and Y is 5. So this means the statement would be 2 plus 5 equal to 12. You see, that's P25 because you just substitute. But you know that this is not going to be true. Okay, so P2 comma 5. Okay, P2 comma 5 is going to be false. So some type of argument would be given to you, then to write it down for us and tell us whether this is going to be true or false. Okay. Any question so far? So it's a kind of new notation that we're going to use. It's a statement containing variables. Okay, and we can operate it as a function. We can have various, values for the X or for the Y. Now, what is going to be next? You see the next kind of notation that we're going to use, that's going to be the crunch of this section that we are going to consider. You see this X and the Y that we use. As you can see over here, you see, the statement that I gave you was X plus Y equal to 12. So you find two numbers whose sum is 12. If you can find two numbers that the sum is 12, this means there exists a value of X and the Y, if you like, that this statement is true. Or there exist some values of the X and the Y for which this statement is false. So we are going to have a special notation for this type of argument to tell us for how many X this statement is true, for how many X this statement is false. This type of notation, if you like, would be classified as quantifiers. Quantifiers because we're going to talk about quantity of this X and the Y. So what is going to be this Z, that's a Q, quantifiers. We are going to have two types of quantifiers, and that's it. So given a predicate, suppose this predicate is given to you, whatever it is. Given a predicate P of X, the statement, look at this one. The statement, what is that statement? The statement is there is some X such that Px. There is some X such that Px means there is a value of X for which P of X is true. You see, that's going to be one. So, or sometimes they express it in this format, or what is going to be the other format that is talking about it? It's equivalent, or for some X. For some X means for some value of X. X, Px, okay, Px is true. Okay, Px is true. It's the same thing. Okay, or there is a value. There is a value of X. A value of X such that P of X is true. P of X is true. Okay, all these type of example. So this means there is at least one value of X for which P of X is true. Means there may be more, but we know that there is going to be at least one. If all these given to you, we are going to call all this statement is going to be denoted by the following symbols. Okay, the symbol is there exists. This is the expression. There exists X, Px. So you should be able to read this one. Instead of writing all these arguments, that's it. There is XPX. There is XPX means the other one. there exists a value of x such that the px is true. For some x, px. For some x, px. There is an x, px. The px depends what it is. You see, the px would be given to you. Then you can go on and find out what is the px is going to be, okay, is about. So we write all this expression like there is x px and is going to be called, and is going to be called, okay, that's an expression that you have to know. We're going to call it the existential, okay, how do you pronounce it? Existential quantifiers. Because of that, there exist quantifiers. Okay, so when we talk about the existent one, okay, there exists x px. This is it. This is the notation, and this is going to be the equivalent format in, okay, in word form. Question? Get to know it. It must be in this direction. Some people write in the other way around. No, there exists x px. It's a very popular notation in mathematics. Okay, so this would happen most of the time, or sometimes when we talk about different theorems. So instead of writing these long expressions that there is a values of x such that the px is true, simply say there is x px. That's it. The machine will understand it, or we understand it what we are talking about. Okay, so this is one question. There is another one. Let's have both of them. So similarly, if you like to get the other one, similarly, sometimes we have some expressions. Oh, for all x, p of x is true. For all x. In this case, you have at least one number. But if it's going to be true for other, so for all x, so similarly, the statement. Similarly, the statement. A statement like for all x, for all x px, you see, for all x px, or for all value, for all, okay, for all values of x, px is true. Sometimes for some theorems, you know that it's going to be true all the time, or sometimes it may be true only for one value. If it's going to be true forever, we say, oh, this is it for all x px. Okay, if this is going to be the case, and now this is going to be denoted by, is denoted, notation, by, the notation is this for all. Okay, for all x px. So as soon as you see this expression in mathematics, you know what we're talking about. This means for all x in the domain of the function, if you like, p of x is true. Depends what is p of x. Okay, what is going to be p of x? Now this one is going to be called, and is called, it's going to be called the universal quantifier. That's the expression, universal. Okay, we call it universal quantifiers. So the universal quantifiers, that expression for all, okay, for all, but the existential one is there exists. You see these two that we are going to talk about. You see this is the one, and the other one is for all. So this, as we talk about it, this is going to be the existential one. That's the one, exist, potential, and this is universal. Universal quantifier, if you like. Okay, that's quantifier and the quantifier. So when you put this in front of any predicate, that would give us the idea what's going to be happen. And we are going to use it in all sorts of theorems. Anything you want to talk about it in mathematics, you can use this instead of writing all the expressions all the time. Okay, so make sure you know how to write it down. Okay, write it down, and then how we're going to apply it quite a lot. The next chapter, use it all in all the proofs that we're going to have. Any question? I give you example to see how we work with this for the time being. Just make sure you use the correct notation and the expression that we are going to know we are going to use. Let's give you quickly a couple of examples. These are going to be in 3.1 so far. So we have the following example. Okay, let's have the first one. The first one is an predicate would be given to if p of x. If p of x is this fact, remember not equal to, it's just a statement, is the fact that the x plus 2 equal to the 7. Okay. Remember, this is an equation. You can solve it. If you solve it, what's going to be x? X plus 2 equal to 7.
5.
5. So as you can see, x equal to 5 is the solution. So this means this equation is true for x equal to 5. So this means there is an x that's such that px is true. You see? So if this is going to be given to you, then, okay, then as you know that x equal to 5 is a solution. Is a solution. Therefore, you can write this, okay? Therefore, there exists an x, okay? There exists an x such that px is true. There is x, px. So this in this part means what? This means the statement is true. The statement is true for one value, okay? It's going to be true for one value of x, for x equal to 5. Okay, this is the way we are going to describe this conclusion, just to get the notation that we're going to have. You cannot say that for all x px. You cannot say that this statement is true all the time, because you know that if you replace the x by 10, 10 plus 2 is not equal to 7. Okay, so you note that in this case, this statement that for all x px is not true, is false. Because this statement is true only for one value, okay? It's going to be true for one value of x, not for all value of x. This is the way you use this, this statement. Question? Give another one. Just compare them together. Look at this one. Already. If this statement is given to you, look at this one. If q of x is this statement that x plus 1 squared, you know that if you FOIL it, that gives x squared plus 2x plus 1. You know that this is an identity. This is an identity. For which value of x this is true? Any suggestion? X plus 1 squared is x squared plus 2x plus 1. Can you tell us for which value of x this is true?
All values of x?
All values of x, yes, because this is an identity. Okay, so this is going to be the one. Then we know it. Then this statement is going to be true, okay? Then the statement, okay, is true for all values of x. So in short, you can say that for all x, qx. This means this statement is going to be true all the time. Okay, so this is a difference between these two together. We have to give you more technical examples. I think I'll be doing it next time. So we'll leave you think about it a little bit. So what we are going to do, we finish it the next time, but we have a couple of very interesting arguments. The way we are going to use these ideas, first we give you some statement in word form. You change it to the symbolic form for us, and some symbolic one into the word form, which is going to be quite lots of fun. Sometimes the way you write it down, so I need more time to talk about it. And the other one is when we use we want to prove these theorems. Every theorem in this book would be in the form of this type of argument that we have over here. And very much we are going to be interested in the negation of these statements. So we are going to give you a kind of remember the De Morgan law that we talk about it? The negation of the P or Q was the negation of the P and the negation of the Q. And the negation of the P and Q was the negation of the P or Q. We are going to apply it here into the very nice format, and that would be very useful for us. Then we finish it. So we need most of the next lecture to be able to finish it. So that would be enough. Just read those valid arguments, take care of it quickly so that we get enough time to take care of this one. I can post your practice test number 1 so that you have a look quickly, because we have quite a lot of these type of problems on that one. So you can have a look. When I go to read, you have the, you already got some idea. Okay, that's one. And I finish grading your quiz. I'm going to start working on today. So you should see the result. Okay, that's it for today. Any question? Have a good one and see you on Wednesday. Bye-bye.
Thanks. See you Wednesday.